Hello everyone. In today's video, we will prove that the kth root of n, whenever n is not a perfect kth power, is irrational. This includes the numbers like root 2, the cube root of 6, the 2021st root of 2021. To do this, we will use the method of contradiction. So suppose that the kth root of n belongs to the set of rationals for some value of n and k. Then, by definition of rational numbers, we can express it in the form p by q for some integers p and q. Q, as we all know, is a non-zero integer. Note that the fraction p by q is irreducible. It is in its simplest form. So the HCF of p and q is 1. The fundamental theorem of arithmetic lets p and q have some unique prime factorization of their own. Say p is a1 raised to b1 into a2 raised to b2, so on and so forth till we reach some ai raised to bi. Similarly, we can equate q to say c1 raised to d1 into c2 raised to d2, so on and so forth till we reach some cj raised to dj, where ai's and cj's are the prime factors of p and q respectively, and bi's and tj's are the exponents to which each of the prime factors is raised to. Because p and q are co-prime integers, they do not share any common factor other than 1. This implies that we cannot find any factors from these that are common in p and q because they are co-prime integers. Even if we raise p to some integral power x and q to some integral power y, the only thing that changes is the exponent to which each of the prime factors is raised to. By doing this, in no way we are introducing a new prime factor, and because initially we weren't able to find any prime factor that is common in p and q, we still are not able to find any prime factor or any factor that is common in p raised to x and q raised to y. So if p and q are co-prime integers, p raised to x and q raised to y follow the same path. This is the key to solving our main problem. Because the kth root of n is p by q, if we raise both the sides to the power of k, this is what we get. N is p raised to k by q raised to k. If we multiply both the sides of this equation by q raised to k, this is what we obtain. N times q raised to k is equal to p raised to k. Clearly, because the LHS is n times q raised to k, it is perfectly divisible by q. Because the equal to sign binds n times q raised to k and p raised to k, there is no chance that p raised to k can escape the grab of q once the LHS is a multiple of q. Therefore, q divides p raised to k. However, because p and q are co-prime integers, q raised to 1 and p raised to k must be co-prime integers using this property. Then how can you expect two co-primes to be friends? How can you expect p raised to k to be perfectly divisible by q? Because it does not even have a single factor that q has in it, as they are co-primes. But there's still hope only if the coefficient of p raised to k agrees to be a multiple of q. And what is the coefficient of p raised to k? Yeah, that's easy. It's simply 1. if q must divide 1, the only values available for it are plus minus 1. But if q holds the values plus minus 1, the first equation changes to plus minus p. Now if we raise both the sides of this equation to the power of k, n is equal to the kth power of plus minus p. But if you read the first line, it says that n can't be a perfect kth power. That is what we started with. So clearly this is a contradiction, the result of our initial assumption that the kth root of n is a rational number. Therefore, we conclude that the kth root of n, if n is not a perfect kth power, is irrational. Once we prove this, we also realize that the kth root of n is either an integer or it is irrational. It cannot belong to the space that separates these two sets. Namely, it cannot belong to the set Z complement intersection Q. If you like this video, give me a thumbs up with any of your fingers. Share it with your friends and everybody around in fact. So bye bye.